Hello and welcome to part 2 of Dev Maths and Statistics Refresher Course, Lecture 10. Now we're going to move on to looking at details of how probabilities are calculated for different types of test and technique. I will not read out every part of these notes, so I'll leave you to read this for yourself because I think maybe it's more effective that way, and I'll just concentrate on certain things. So the first technique I want to pick out is confidence intervals. And confidence intervals are really, I think, very simple, probably underused by many students because they're quite simple, but I would really encourage you to use confidence intervals really almost every time you have a sample. A confidence interval is a great place to start before you get into more sophisticated tests when you have scale data. So the situation is you have some observations, so sample size of n, and these are the observations, and the population has got unknown mean mu and standard deviation sigma. Now the interest here is in estimating this, what is this unknown mean mu. We know that the sample mean x bar is the blue estimator of mu, so in other words it's the linear unbiased estimator with the lowest variance, and that's based on calculating from these values here. Because we can't calculate mu directly, you can only calculate the mean of these numbers, which is x bar. So we know it's blue, so it's the best estimator we can get with a linear combination of these sample variable values. But we also know the probability of selecting a sample so that the sample mean is exactly equal to the unknown population mean is very low. In fact, as the footnote says, for continuous variables it's 0. So always you're going to be a little bit away from the population mean. Because it's blue, we expect it to be near because the variance is low, but how near will it be? And the confidence interval gives you that information. It says how near to this unknown population mean can I be confident that I've ended up. And it's based on this distribution of a random variable that follows the t distribution from the last lecture. What I showed you in the not quite normal demonstration was that when you extract lots of samples, then the mean of the sample is the x bar. This is the unknown population mean, so you're looking at the distance from where you've got in your sample to the unknown population mean, and you're counting that in terms of how many standard errors is that, and the standard error is the sample variance divided by the square root of n. So as n gets bigger and bigger, standard error gets smaller and smaller, so the t-values get larger. And so the t-value is a random variable, because sometimes you're going to be close to the mean, sometimes far away. This is also, S is also a random variable, which introduces some extra uncertainty. That's why it's not Z, it's T. So T is varying depending on how close you are to the actual population mean. But because T is a known distribution, for as long as we know the degrees of freedom, the sample size, then the T distribution is known. We can calculate the values of T so that what's called the critical values of T, from negative T critical to positive T critical, because it's symmetrical, we can calculate what these values must be so that there's a range in between of 95% of the values of T, and only 2.5% are bigger, 2.5% are fewer, lower than that, and 95% is between these values. If we do that, then we can rearrange this equation here, rearrange this and substitute into the inequality. You can find this. So for 95% of the values of t that you get, the unknown population mean will be within this distance, standard error times the critical t value. So starting from the mean of your sample, you subtract that. Starting from the mean of the sample, you add that, and that gives you your confidence interval. Okay. Best is just to look at examples of this. So here we've got a situation where we're talking to people in an urban market and you have a very small sample, 6 people. You know their earnings on the previous day, but based on that you can say, okay, what's the confidence interval for the mean daily wage in the whole population of all these casual labourers? So first of all you calculate 6.65, and here, just to check, you have to be clear what this is. This is the sample mean. This is only the mean earnings of these 6 people on the previous day. It's not the same as the mean earnings of the whole population. But we think it's going to be near, but how near is the question. So that's what the confidence interval will tell us. So the ingredients you need the mean of the sample standard deviation is based on these 6 numbers. So you do the standard deviation calculation, but dividing by n-1, so divided by 5. Then once you've got this value, that's for individual values, then because we're taking a sample, that reduces the variance on the standard deviation even more. So you divide by the square root of 6. So this divided by square root of 6 gives you the standard error. And then you look up in Excel, it gives you the formula of how to do it there. And the footnote how to use Excel to do that. Look up the critical value of Excel, so you know that 95% of t-values for a sample of size 6 are between negative 2.57 and positive 2.57. So now you substitute the critical t-value, the standard error and the sample mean into this equation, and you find that the mean, population mean, is between 5.44 and 7.86. So you could be 95% confident that the population mean for all the labourers in that market is between 5.44 and 7.86 taka. So it's a wideish range, but based on only 6 people, you can now say something with 95% confidence about the whole of the population of that market, which is really quite powerful. Before we look at other ways of calculating this and other examples, let's just think about these things here. What affects the width of this? So you might, if you look at this equation 1 and equation 2, you can see what would affect the width. And clearly the critical value, t, that would affect the width. So the bigger that gets, and what affects that is the confidence interval you want, the confidence you want to have. So if you go for a 99% confidence interval, then these t critical values need to be further apart because you need 99% in the middle. So these get bigger. So these get bigger, so the confidence interval gets wider. If you increase your sample size, so bigger sample to base things on, you'd imagine that's going to give you a narrow interval, more information. So you can see that from here, that as n increases, the standard error decreases. So the t values get bigger. As standard error increases, that increases this directly here. So it's affected by this, which depends on confidence level you choose, 95, 99, 90, 85. That makes it wider. Increasing the sample size brings the standard error down, so that reduces this, so that makes it narrower. So bigger sample makes it narrower. Those two things are both within your control. You decide the percentage you're going to use, and you decide the sample size. The thing that's not in your control is the size of S. And as S gets bigger, standard error gets bigger. That makes it wider again. And S depends on how spread out your sample is, which really depends on how spread out the underlying population is. So when there's a lot of variation in the underlying population, usually you're going to get more variation in your sample. S will be larger, so you're bound to get a wider confidence interval. So that's just inevitable. So when there's a lot of variation, you need to combat that by maybe increasing your sample size. Okay, and then before I show another way of calculating this, let's just look at what confidence actually means. What does it mean to be 95% confident? Well, it explains it there, and there's a fantastic demonstration which I'll link to in the notes. Confidence interval of sample mean, it's almost as good as the sampling demonstration. So what you have here is a situation where The unknown population mean is 100. You can change that here over on the left. Unknown population mean is 100. And you can select the confidence interval, the sample size, so for 6, so it's the same as the one we've been doing. Confidence interval 95. What it does is, it selects 100 samples of size 6 from this population randomly, and it goes through those same calculations and calculates a confidence interval. So for example, this one on the bottom, it said, okay, based on the first sample here, I can be 95% confident that the unknown population mean is between here and here. And then it does it again and again and again and again and again. However, you notice that sometimes, like with this case here, you get the sample, you calculate the 95% confidence interval, you say, I'm 95% confident that it's between here and here, and you're wrong, it misses. That's why it colours it red. This one also missed, this one missed here. You might wonder why it's such a tiny one, that must have had a very small variation in the sample. This one's quite large, but it missed as well. So 1, 2, 3, 4. 4 times we've missed out of 100. And what the 95% confidence means is that if I do this 100 times, then I expect that 95 times out of 100 I would successfully capture the population mean. But unfortunately, about 5 times out of 100 I'm going to miss. You can just repeat it by doing another 95, another 100 samples. So here, 1, 2, again, it missed 4 times. Interesting. Here it missed 1, 2, 3, 1, 2, 3, 4, 5, 6 times, so slightly more than you'd expect. Okay. If you increase the confidence level to 99%, and then, so that's, in that case, it would have got, using the same data, that gets all of them. Resample, just 1 missing. So with 100%, you expect to miss about once every 100 times. Oh, that's a very bad with 3 misses. There's no misses, so there's some variation there. There's 1 miss. So that's the interpretation of a confidence interval. It means if I went and got 100 samples like this, then I know how many I expect to capture the true population mean. Downside is you don't know whether your sample is one of the lucky ones or one of the unlucky ones. That's just how probability goes. So one other way of doing it is that instead of using a calculator, for practical work, you don't want to use a calculator if you have many numbers. So for practical work, you can do the calculations with a spreadsheet, and there's one here which, again, I'll give you the link to this, but it just has the formulas that I'm talking about there, just built into the spreadsheet. But this is just a convenient form, so you can just paste the data in. So I've already just got that data for those numbers there. Actually, I even copied it already. So I'm just going to copy that. So that's the data from the example I just gave you. If you paste it over this data here, then it does the calculations, see the numbers agree, and it comes out with the confidence interval from, let's put it up a bit, paste in the data, and it calculates the confidence interval for you. So all the steps are in there. Sometimes if you don't have the actual raw data, if you've already worked out the things you need, which is the sample mean, and you need the sample mean, the standard error, and the n, the sample size, you could just put that directly into the next version here. Yeah. So instead of starting with the data, you start with those numbers, sample mean, standard error, and n. Type that directly in, and it calculates the confidence interval for you. So that's available. Or, as I'll show you later, you can just calculate it in Stata very easily. So next, I'll just show you how you could use confidence intervals to address that example we had in class of reading and rice. So if you find this, you could try this with the sample that you took. But this was the sample that I took, that I put on onto the class results. And what we had here was, it seemed as though in 2005, it's my breakdown, there's a difference between the females and the males in 2005. But this is in the sample. So what you want to know is, if you took that as the mean for the men, if I look at this mean here, can I be confident that the mean for the females in the whole population is different from the mean for the males in the whole population? So to answer that with confidence intervals, instead of just calculating the 741, which is the sample mean, I could work out a confidence interval. So I'll just get these numbers. put them here. And just bring them together by using sort. Okay, so that's the females in 2005. And then let's look at the males in 2005. If this, you can just whiz through if you want to get to the, just think step by step, but you can fast forward. So let's work out the confidence interval for the male-headed households first. So if I just take this and superimpose it on here, then it does the calculations. It says that, okay, based on this data for men, so this is the confidence interval for men. So this is 205 men. Between there and there. So based on the sample of men we have, which is I think 31 male-headed households, we could be 95% confident that in 2005, for all the men from that whole population, all the male-headed households, the population mean was somewhere between 734 and 787, whereas for all the women, remove this, it's too much data. Oops. For all the women, the confidence interval is this. And so the true mean for all the men is, we're 95% confident is in here somewhere, and for women it's in here somewhere. But as we can see, there's a very big overlap between these two. So the women's mean could be anywhere from 650 up to 833. So wherever the men's is, it could be the same as the women. Women could be higher, women could be lower, could be the same. So this data for 2005, even though we see this difference in the sample means, when we consider the confidence interval, it tells us that we cannot be at all confident about how to compare the population mean between men and women in 2005. Let's just make a comparison of that with what happens if we look at 1975. So data. So again, I encourage you to use the fast forward button. I'm just going to do exactly the same thing for 1975 by getting the data for the females, which is there. And for the males, which is this. And let's find the confidence interval for the males first. Actually, it's simpler to find for the females first because there's fewer of them. So for the females first, so here's the mean, 568. As for that, so that's this value up here. But the interesting thing now is you've got the 95% confidence interval. It's somewhere in this range. So this was women in 1975. And then men in 1975 is this lot. And here's the confidence interval. So now we've got a difference. You can see that back in 1975, we can be 95% confident the yield for women is somewhere in here, and the yield for men is somewhere in here, but there's no overlap. Because there's no overlap, that's pretty strong evidence that they were different in those days. In fact, that men's yield was above the women. So in 1975, just looking at that one sample, we can be confident that the men were producing more, but we're looking in 2005, we can't be confident. So it asks the puzzle of when we look at the class data, when you only have your one sample, this is one way that you can be either confident there has been a difference, there is a difference between two groups, or you can see that it's not certain, you can't be sure there's a difference in the two groups. So this confidence interval is one simple technique of being confident about making group comparisons. So I'd really encourage you to present these. And really, any time you present any data like this, instead of just saying, the mean of this was this, the mean of this was this, also give the reader the confidence interval, because the reader then knows, okay, I've seen the sample mean, but that is telling me that the population mean is somewhere in that range, and that the reader themselves has a lot more insight into what's going on. So please use confidence intervals, whatever other tests you carry on to use afterwards. Okay, so in the next part of the lecture, I'll go on to look at some of the different kinds of tests that we can develop. But for now, thanks for watching.